Today I'm going to talk about global weak solutions for modified Kamatsumi equation. This talk is based on two papers written with Li Lei, Liu Jianguo, and Liu Hao. And okay, let's start. So this is the modified Kamatsumi equation. This is a 1D PDE, and we have two unknowns in this equation, M and U. This is in the mass transport form. You see, the velocity field is u squared minus ux squared. And these two unknowns are related by this Helmholtz equation in 1D. We will talk about this Helmholtz equation in 1D later. Okay? This equation was proposed by several different authors in different years. And why we call it as a modified Kamatsumi equation? Because of the following relations with the KdV equation and the modified KdV equation and the Kamatsumi equation and the modified Kamatsumi equation. Okay. All these four equations, they are integrable systems. They have Lax pairs, bihamiltonian structures, and infinite many conservation laws. Okay. For the MCH equation, we have local existence and uniqueness of strong solutions. And we can also show for some initial that the strong solution will blow up in finite time. It's like a Burgers equation. Okay. So the question is how to extend weak solution globally. Okay. So first, let's say a little bit about the definition of weak solution. Okay. Here we write all the terms into terms of U. Okay. I use the relation, of course, Helmholtz equation. M equals to U minus UXX. So the first term is actually empty. And this term is also M. Okay. So we write into terms of U and take all the possible derivative out and multiply with the test function and use integration by part. We obtain this function. And here is the initial that. Okay. So if a function U satisfies this relation for any test function, we will say this U a global weak solution for modified Kamatsumi equation. Okay. We will skip the spaces such that all this term holds because we will see the spaces from some special weak solution later. Okay. So to introduce some special weak solution, let's first study the fundamental solution of Helmholtz equation. Okay. So M and U are related by this Helmholtz equation. We have a fundamental solution 1/2 into the power negative epsilon value of x. With this fundamental solution, U can be written as the convolution of G and M. And here is the picture. Here is the picture of G. This is not bad. This function. It's global lipschitz. It's L1, L infinity with bounded variation. Here, that's the total variation of G. Okay, and but at the top, it has a peak. Okay, so the derivative G prime has a jump at 0. So we don't know the value of G prime at 0. Actually, it's very important to decide this value. For weak solution. Okay, it's different with the Kamatsumi equation. For Kamatsumi equation, you only need to set G prime 0 as 0 as the average left and the right limit. Okay. But for modified Kamatsumi equation, it's different. Okay. So, as we know, for Kamatsumi equation, we have this kind of weak solution, which is known as M-Pekin weak solution. It is in this form. Why we call it Pekin? Because of the picture of this G. At the top, we have a peak here. So we call this kind of a solution as M-Pekin solution. For Kamatsumi equation, this PIT and XIT will form a Hamiltonian system. But here M is just UN minus UXXN. It is a combination of some delta function because this delta comes from G minus GXX, right? Because G is the fundamental solution of Helmholtz equation. So we have a delta. For MCH equation, we can also try to obtain the system for PIT and XIT, by taking this form of solution into our definition of weak solution, U5, and initial that. And after some calculation, you will find Pi a constant. Okay, and Xi satisfy this this system. But we can only use this system before the trajectory collide with each other. Okay, before the collision time. Okay, we can use this system. Okay, when n equals to 1, this is a solitary wave, special solitary wave. Sometimes we call this as a Pekin solution. Okay, the traveling speed from this system, when n equals to 1, all these three terms disappear. We only left p squared over 6. So the traveling speed is p squared over 6 for Pekin solution. Okay, so we can provide a simple example for when n equal to 2. I will split this part. Because when n equals to 2, the system will be very simple, and you can prove the trajectory will collide with each other in finite time t star. Although we can obtain global trajectory x1t, x2t, although we can obtain global trajectory, but if you use this global trajectory to construct two Pekin solution, it is not global weak solution. It will not be a weak solution after T star. Okay, that means we can only use this system before they collide with each other. So the question is how to obtain global trajectories for n Pekin solution. How obtain global n Pekin solution. Yeah. Is there any noise because outside do construction? Okay. So let's see where is the problem. Let's start from a characteristic equation. So the velocity field is u squared minus ux squared. So when u is in this n Pekin special form, we have un squared minus unx squared. We have these two terms. So for the first term, it's okay because g, we know g is global limited. So this term is global limited, and but this term we have trouble. This term because we know this term contains g prime term, and we know g prime has a jump discontinuity at 0. So exactly for un because uxn we have a jump exactly at xi equals x equals xit. So the question is how to determine this value to give global trajectories. Okay, so we have a wave field that is non-linear. So next idea is to do some. Sorry, there's some noise outside. Let me put my cell phone on. Okay.
Can you hear me?
Yes, we do.
Okay, so a natural idea is to do some modification, right? We try to modify the velocity field to obtain global trajectories. This is like the vortex-blob method for 2D Euler equation. Okay, so let's see how to do that. Let's start from one Pekin. Okay, so because one Pekin we know the traveling speed is exactly p squared over 6. Okay, so we let's calculate the characteristic equation. We take one Pekin inside. That's u squared. This is ux squared, and we will have these two terms, g squared at 0 and g prime squared at 0. The first term we know it's 1/4, but the second term we don't know. However, we know the exactly traveling speed is p squared over 6. So this gives us the definition for g prime squared. So the definition is 1/4 minus 1/6. That's 1/12. So if we define G prime square at 0 is 1/12, then we can obtain the correct traveling speed for weak solution. Okay. So the question is, how can we do modification for this term to obtain 1/12? Let's try a little bit. So we take the standard modifier, even function, integration is 1, and the rho epsilon defined by this, and the G epsilon is the convolution of rho epsilon with G. So for G prime square, we have two types of modification. The first one is you modify it first, and then you take square. The second is you take square first, then you modify. Both of these two methods cannot give the right speed. The limit, the first one is 0, the second one is 1/4. This is basically because G prime is this one, this BV function. Here is 1/2. You take square, you will obtain this one. Here becomes 1/4. That's gx squared. That's gx, and you modify a BV function and then take the limit. You will obtain the average of left and right limit. Okay, so the first average is 0. The second average is 1/4. They are all not 1/12. We 1/12. We want 1/12. Okay. Fortunately, if we put them together, put these two type modification together, we will obtain the correct traveling speed. That means we modify G first, and then we take square outside the first step, the second step. Outside, we modify again. Okay, double modification. Okay, double modification will obtain speed. The proof is I will skip the proof, but the proof won't depend on the rho epsilon. Okay, for any modifier, even function, you can prove this. Okay, so this is the key idea. This implies how we can modify the velocity field. Okay, so 3 steps. First, you modify un, and second, you put them together, square together, and the third step, you modify again. Okay, double modification. So now our velocity field is global Lipschitz. We can obtain global approximated trajectory, SI epsilon. Okay, and our modification will avoid collision. Okay, avoid collision. So first, let's we think about the initial data in this form. Initial data, Ci is initial position. This sigma pi is the total variation of M0n. Total variation. Okay, so this condition is important. We will use this later. And so initially, if they are well separated, then the approximated trajectory, they will never collide with each other. Okay, they will never collide with each other. And so now we have a global approximated trajectory. We can construct approximated M-Pekin solutions, right? Approximated M-Pekin solution. Use these global trajectories. So the question is, how far is this approximated trajectory M-Pekin solution from the real weak solution? So let's take this inside our weak formula, the formula for weak solution, and calculate a little bit. If this is 0, then it is weak solution. Okay. However, it is not 0, but not far from 0. We calculate, and it is less than some constant multiply epsilon. So that's great, right? That's a weak consistence. If one epsilon goes to 0, we have some un. That perhaps this is a weak solution, right? Perhaps this is a weak solution. So now let's do some companion argument. We first see, is there any limit trajectories for xi epsilon? Then use that limit to construct global M-Pekin solutions. So fortunately, we have because un, you see the velocity field is un square minus uxn square, and the un is in this form, pi gx minus xit. So because g is 1/2 e negative x epsilon value, so this one is less than 1/2 sigma pi. Remember, we have the total variation bound, which is m0. Okay, un is a bounded function, and similarly, ux is also bounded. So the velocity field is actually bounded by m0 squared over 2. Okay, this term. So global Lipschitz, the trajectories are all global Lipschitz. So we have uniform boundness and equicontinuity for these trajectories. Then we use a theorem to obtain limit trajectory. Okay, limit trajectory. Okay, with this limit trajectory, we can construct a limit function un, and by almost everywhere convergence, we use the Lebesgue dominated convergence theorem, we obtain this L1 local L1 convergence. That's in space-time. This is enough for us to pass to the limit in all the terms in this functional. Okay, this is enough. So we obtain a global n-Pekin solution. We obtain global n-Pekin solution. After we obtain global n-Pekin solution, we can use mean field limit method to obtain global solutions for other for any initial Rod-Meyer. Okay, how to do that? We can choose some initial that in this form. That's m0n, and to approximate our initial that in Rod-Meyer. And this kind of initial on the left hand side, we can obtain global n-Pekin solutions. And then we do some space-time BV estimate. We can obtain some limit u, and then we can prove this is actually the weak solution for initial data m0. That's a mean field limit method. Okay, I will skip the details. And moreover, our method can be generalized to the another family of equation, generalized modified Kamat-Zinn equation. Here, the power is any arbitrary positive integer. This is a highly nonlinear equation. However, we can still use our double modification method. Modify one time and take all the power, and then modify again. And this method, from this method, we can obtain global weak solutions for this family of equations. And this method is very easy to calculate the traveling speed for solitary wave. It's very easy to calculate. If you use traditional way, you need to put it into the weak formula to calculate this traveling speed. But you see, because the highly nonlinearity, the weak formula is not that simple. Okay, so that's all for my talk, I think. Thank you.
So thanks for Goyus for the inspiring talk. So any questions?
Yes, I have a question. On your page 16, you show that the trajectories.
I'm sorry.
On your page 16. On your page 16.
Dr. Goyu, can you hear us?
It's my problem, I think.
You cannot hear us?
When I put in the...
You can only speak out.
Okay,
can you hear me?
Yeah, I can hear. Okay.
Oh, okay. So on your slide 16.
16.
Yeah, you claim that the trajectory never cross with each other. Could you let me know more?
Okay. Yeah. Because we have proved the approximate trajectory that are well separated.
Okay.
So the limit that can never cross each other, right?
So what is the mechanism behind why they are always separated?
Or
or the reason, or or in analysis, how to see
The
this
analysis,
easily?
we only need to show this kind of analyze, right? This kind of one. Right? If we obtain this inequality, then they are well separated.
You mean the distance square can never take 0?
This is a 1D case because that's initial position. Initially, they are well separated. Yeah. So from this one, we can obtain xk plus 1 epsilon minus sk less than equal to some bigger than equal to some
Yeah, they never reach 0 from multi-type
Okay,
argument.
so I see.
Yeah, they will never collide with each other. Yeah.
I see. Because I see your condition there, I suppose there should have some reason why you use the condition. Okay, I got it.
Okay, any more questions? Okay, so I have a question for you. So for the weak solution you construct, so is it unique?
Oh, that's a very good question. We have tried we have tried put the limit, right? When epsilon goes to 0, we try to prove we have a unique trajectory, but we didn't get that. Another thing is this kind of solution does not preserve the energy. I think that's the key problem. Sometimes the energy increase, sometimes dissipate. I think that's the problem. Yeah, the key problem. We don't have uniqueness. Yeah.
I see. Okay, any more questions?